Okay, so we're going to continue on with chapter 8. And this is a bit of a strange chapter. So we'll be thinking about, instead of looking up at the sky, we're going to be looking down at the dirt and doing a bit of geology, thinking about Earth as a planet. So even though we live on the Earth, it still is something in space, and we can take away a lot of important lessons by examining it closely, in particular because we're able to actually see details here that would be much more difficult to see on other planets. Um, so where do we start? Well, we want to understand what is unique about Earth and what is pretty common about Earth. So Earth is in a nearly circular orbit, so it's not very, ovular. It's nearly circular, in the Goldilocks zone around the sun, which means that we're in a place where we have good temperatures for life as we know it, which of course we're very, biased in what we mean when we say that. Earth is covered in liquid water, over 70% of the surface. It's a fairly medium-sized rocky planet in terms of what we've seen in other solar systems, but we'll talk more about the difficulties with that a little bit later. So it's got a diameter of about 13,000 kilometers and a mass of around 10 to the 24 kilos. And like I said, we're going to use Earth as a testing ground for some of the ideas in astronomy and astrophysics that we want to apply elsewhere, both in our solar system and throughout the universe. So what is inside of Earth? Well, we've never really looked inside of Earth other than in relatively shallow holes. So we have to get creative, and basically, whenever there's an earthquake, seismic waves, which are basically just sound waves in the rock, are able to pass through the entirety of Earth. And with modern tools, we can actually detect the waves from an earthquake, not just nearby where the ground is shaking really, obviously, but also quite far away, even on the opposite side of the Earth. And so in order for the waves to get there, they have to travel through all the different parts underground. And whenever the material changes, or whenever there's a boundary between layers, there can be reflection and refraction of these waves, just like what we talked about for light waves. And so using this, scientists have been able to map out what Earth is made of, and we've used this in astronomy to analyze other planetary bodies, both comparing and contrasting them to Earth. And so importantly, humans have never physically sampled anything beneath the crust. The deepest holes we've dug have barely penetrated Earth's crust, but we nonetheless have quite a bit of detailed information about what's under there thanks to these seismic waves. So what do we find? Well, you've probably heard this story before, but we find that Earth is made up of different layers. And whenever a seismic wave goes through one of these layers, it gets bent. And so that's how we're able to map out where these layers are and what they're made of. So the crust, this is the sort of rocky outer layer that we're all mostly familiar with. Beneath that is the mantle, which has a few sort of subdivisions. But in general, the mantle is, people imagine it as a liquid like lava or magma, but it's actually fairly solid. It's a very slow flowing, it's a complicated type of material where we have very hot rock that wants to be liquid, but it's under so much pressure from the weight of the Earth above it that it is nearly solidified, but it can still very slowly flow. And we'll talk about why that's important later when we get to plate tectonics. Beneath the mantle is the core, which has two different divisions, an inner core and an outer core. So the outer core is made of primarily liquid metals, and this is what, as we'll see momentarily, gives rise to Earth's magnetic field. The inner core seems to be solid metals, and it's much more mysterious in terms of what it's actually composed of. It's the part of Earth that's sort of hardest to study due to the shielding of the other layers. So like I mentioned, because we have a liquid outer core, so whenever you have a liquid conductor, you can actually get sort of self-perpetuating magnetic field generation. And this is a complicated topic in physics, but effectively what you should remember for this class is that a liquid inner core, or a liquid outer core in the case of the Earth, gives rise to a magnetic field. So if there's no liquid, there's no magnetic field. And so Earth's magnetic field is really nice for us as humans. So for one thing, it means we can use a compass to figure out roughly which way is north and south. But it also provides some protection to us from the solar radiation, which is mostly high energy protons that the sun spits out. We call this the solar wind. And so Earth's magnetic field causes the solar wind to be bent around Earth and to be trapped. And some of it gets concentrated at the poles, which we see as the aurora borealis in the north and the aurora australis in the south. So zooming in on the crust a little bit more. So Earth's crust is mostly made of rock. And when we look at this rock, it has, there's a lot of different variations, as you will learn if you take a geology class. But in general, most of the rock is either basalt or granite. So oceanic crust, so the parts of Earth beneath the oceans, tend to be made of basalt. And the parts of Earth that are not beneath oceans, the continents, tend to be made of things like granite. So both of those are what we call igneous rock. They both come from cooling lava, which is this material from the mantle. When it gets to the surface, it's no longer under pressure, so it becomes much more liquid. But the rate at which this cooling happens determines the structure of these rocks. So if it happens very quickly, we get, which is underneath an ocean, it will be cooled off really fast. That's how we get basalt. And if it's more gradual, then we get this continental crust, which is made of things like granite. If you ever looked at a granite countertop, it has much larger grains of material and crystals and things within it. So if this igneous rock is broken up into pieces and then recompressed, we call that sedimentary rock. And that's really useful if you're interested in fossils. You can look at the different layers and figure out how old the different fossils are. And then if that sedimentary rock is pushed deep enough within the Earth, then it gets reheated. Remember, the inside of the Earth is quite hot. Gets reheated and pressurized and turned into what we call metamorphic rock, which is just sedimentary rock that's been kind of processed again. So you've probably heard about those before, but in astronomy, we also want to highlight another option, which is primitive rock. And so primitive rock is rock that's left over from the early days of the solar system. And so due to the way that Earth formed, Earth was basically all molten at one point in its history around 4.5 billion years ago. And so no rocks on Earth are primitive unless they come from outer space. So something like a meteorite can be made of this primitive rock. So it's very rare here on Earth, but we can get it this way or through samples from outer space that we bring back. And those primitive rocks tell us, as astronomers, a lot of valuable information. You can imagine those are things that we want to study very closely. Okay, so I mentioned it before that the mantle, it's mostly solid, but it can flow very slowly. And so what this means for Earth is that the different chunks of the crust can move relative to one another, and we call this process plate tectonics. Again, you've probably heard about this in another science class at some point, but I want to highlight a few interesting aspects that are relevant for astronomy that we're going to talk about later. So as plates, you can imagine plates can do 2 or 3 things. So they can move apart. When they do that, they're going to expose new magma that turns into new plates. And that tends to happen in the ocean. So the ocean plates are the youngest parts of Earth's crust. and new ocean plate is being formed all the time as the ocean plates separate. We can also have plates hit each other, and when that happens, we can either have one go underneath, which we're going to see in a moment, which is called subduction, or we can have them push up and create mountain ranges. And so it's important to understand that continental plates are much older and they're much thicker, right? They're the parts of Earth that are above the water, so they're much thicker, and so they tend to always go on top whenever two plates collide. And as a result, the continents can move around on the surface of the Earth, but they don't tend to be subsumed under, the crust. So lastly, we can also have plates just kind of rub against each other. This is very relevant if, like me, you live in California, where we've all heard of the San Andreas Fault. So when that happens, we tend to get earthquakes, right? As we know and love here in California. So where did this idea of plate tectonics originate? Well, people have long noticed, since we had good enough maps, so starting maybe in the 1700s, that the continents, especially Africa and North and South America, look like they could fit together roughly. But of course, that could have just been a coincidence. And so it took until Alfred Wegener basically started piecing together some data for this to become a more popular idea. And what Wegener found was that in, for example, Western Africa and Eastern North America, if we look back long enough ago, so at deep enough sedimentary fossil layers, we see that there are similar animals in both of these places. And we see that sort of animal evolution in both of these places progressed in similar ways. We also find geological features, rocks, that are similar in both of these places. So taken all together, and with our modern knowledge of how plates can move around due to the magma or the mantle underneath, we now understand that back, in the ancient Earth, the continents were all stuck together in what we call Pangaea. And so Pangaea was a supercontinent, eventually that broke apart into pieces until we get the world we have today. And so you can imagine during the era of Pangaea, Earth had one huge ocean. We still kind of do. The Pacific Ocean is the leftover, as the continents have spread out. They've made the Pacific smaller and smaller, but it's still quite ridiculously big, right? Over almost half the surface of the planet. Okay, so, but anyways, this is the origin of this idea of continental drift and sort of how we can map it back into the past. We could also map it into the future and see that eventually we will have the continents collide again and we'll get a new Pangaea. But we've got a long time until that happens because this mantle is very slowly moving fluid. Okay, so what happens when the plates collide? Well, we already had a brief overview, but just to show you some pictures. So if we have oceanic plates, which is what is happening in both of these pictures, that are either colliding or spreading apart. So if they're spreading apart, we call this a rift zone. And that's where the mantle is exposed and we create new oceanic basalt. We create new plate. If the plates are coming together, we call this a subduction zone. So one of the oceanic plates will be pushed below, and that creates these really deep trenches in the ocean. It tends to also create a lot of volcanic activity as well. Okay, and so what if we have continental plates? Well, if two continental plates come together, they're much thicker, so they don't like to subduct. And we tend to get mountain ranges in this case. So a famous example is when India, which is its own plate, collided with the Asian plate, both of which are continental. We formed the Himalayas, which are the largest and tallest mountain range on Earth. Now, over time, so mountains are initially formed. They're very steep and sharp. So think like the Rocky Mountains, a relatively young mountain range. Over time, erosion and weathering cause the mountains to be smooth and to become, rounded and more like hills, and eventually it causes them to vanish. So, the continents we have today oftentimes are made of multiple plates, we don't see the effects of these mountain ranges so much anymore because there's been enough time for them to be worn down and vanish. We will contrast this with other planets in the solar system, which have geological features formed in vastly different ways, and we're going to see how we can tell them apart once we get to later chapters where we study, for example, the surface of Mercury, which is made in quite a different way. Okay, so we also should talk briefly about volcanoes. So of course, if we have plates colliding, this can create places for lava to escape to the surface. So especially in subduction zones, which is near these ocean ridges. And this is how, for example, around the Pacific Ocean, we have what's called the Ring of Fire, which is where a large fraction of the world's volcanoes are located. But I want to highlight a really interesting different method for volcanoes to form, which actually we see in Hawaii, which is a volcanic hotspot, and specifically a core mantle interaction. So deep below Earth's surface, where the outer core and the mantle interact, we can sometimes get dynamic instabilities where the fluid is flowing in a really complicated way. It causes it to heat up. But that heated area, because it's near the outer core, as the continents move, that hot spot doesn't move. And so this is what we see in Hawaii, where the islands in this picture on the left are the oldest islands. They used to be above this hot spot. They used to be where the active volcano is. But as the plate has moved, this oceanic, this Pacific plate, every once in a while, this hot spot will, have some volcanic eruptions and create a new island that then kind of gets conveyor belt shuffled out of the way. And so this is why the current hotspot island, is the active volcanic island, is the big island, Hawaii. And the rest of the islands don't really have any volcanic activity because they're no longer above this hotspot. So kind of a fun example. Okay, so let's change gears a little bit. We've been talking about what's below the surface, but what about what's above the surface? So Earth is also really interesting in that we have a very unique atmosphere, and this is a big part of how Earth is able to support life as we know it. And so we should take a moment to appreciate that we live in a big sea of air, right? There's tons of gas above us, and we can feel it, right? We can feel the wind below. We can see the effects of this ocean of air in the weather and clouds. And we can actually feel it as well through atmospheric pressure. So you'll hear, old people talking how they can feel storms coming due to the change in pressure. We can actually measure that with the barometer, and that's part of how weather predictions are made. We also need this atmospheric pressure to do lots of very basic things, like when you drink your juice box with a straw, you're only able to do that because basically when you remove the air in the top of the straw by sucking on it, the pressure of the weight of the air above us pushes down on the surface of the liquid and pushes it up the straw into your mouth. Now, that pressure has a limit. That's why you can only build straws that are so long until eventually they won't work anymore. So the maximum limit is around 10 meters. Okay, so how much air is there? Well, there's around 10 to the 18 kilograms, so a pretty small fraction of Earth's weight. But this is enough for basically every square inch of Earth to have about 15 pounds of air above it. And so like I say here, this is fractionally, like compared to the mass of the Earth, this is less than the weight of the hair on your head compared to the weight of your body, but it's still quite significant for life and leads to a pretty large pressure, right? 15 psi is nothing to laugh at. So what is the structure of the atmosphere? Well, like inside the Earth, we can also split the atmosphere into some layers. The layers of the atmosphere aren't as distinct, so it's a bit of a naming game rather than a clear boundary sort of situation like we have within the Earth. But just to go through the list, so we have the troposphere, that's the layer that we live in, sort of the lowest layer of the atmosphere, and that's the layer that contains most of weather, most of clouds. It's heated because it's close to the ground, right? Air doesn't tend to be heated much as the sun passes through it because it's fairly transparent. So this lower layer is heated because it just is able to conduct heat from the ground, and that's how it's able to maintain sort of the comfortable temperatures that we're used to as humans. As we go higher up, we come to the stratosphere, which is much colder because it's farther away from the Earth. It also is where we see the ozone layer. So the ozone layer is the upper part of the stratosphere. Ozone is just a molecule of oxygen with 3 atoms of oxygen. And it has a nice property, which is that it is relatively opaque to UV radiation. And so this provides kind of a protective barrier like sunblock for the planet, which is good for us humans again, because we don't have much protection from UV otherwise. Even the little bit that leaks down can still give us a sunburn. Okay, above that we have the mesosphere. Not much interesting happening here, but it is where meteors tend to burn up. So this is where the air just gets thick enough that there's enough friction that small rocks can be vaporized. I should also mention, you'll notice here that the ozone layer is actually warmer than the other parts of the atmosphere. That's because whenever the sunlight, the UV is blocked, it's absorbed. That energy is absorbed, and it causes the ozone to heat up. Okay, so then above the mesosphere is the ionosphere. So that's where the stellar wind gets trapped by Earth's magnetic field in what are known as the Van Allen belts. And it's really important for humans to send long-distance radio communication. So before satellites, we can actually bounce radio waves off this ionosphere as if it were a mirror, due to the fact that the air there is ionized, so that the electrons are ripped off their atoms. And so roughly around that region is where we tend to say that space begins. So there's not really a clear point where we say the atmosphere is over, right? It just gets less and less dense as we go higher and higher. But around 100 kilometers above the surface is usually where people say, okay, you're basically in outer space. At that point, you can start to have low Earth orbits. So you can have satellites that orbit around 100 kilometers of altitude. So what is the atmosphere made of? Well, primarily nitrogen, diatomic nitrogen. Again, very convenient for us as humans because this nitrogen is very stable. It's hard to react with that nitrogen because it has a triple bond. It doesn't want to bind to anything else. The second large chunk of the atmosphere in terms of composition is oxygen. That's much more reactive, right? That's the part of the air that we need to breathe in order for the chemical reactions in our body to be able to progress fully. So in addition to the 2 main parts, we have a bunch of trace elements in the atmosphere. So an important one that we'll talk more about is carbon dioxide, which is a greenhouse gas. And even though there's not much of it, it has an oversized impact, as we'll see in Earth's climate. We also have argon, which is the second lightest noble gas. So it's highly non-reactive. It's used in welding, for example, to prevent oxidation. And then the kind of wild card in the atmospheric composition is water vapor. So you probably have already encountered the fact that water vapor can really wildly vary, right? This is what we call humidity. So we can have quite a bit of humidity, maybe 4% of air, or we can have almost none, down to near 0%. And most of this water vapor is in the troposphere, this lowest layer. And as we go higher into the atmosphere, there's less and less water vapor. It tends to precipitate out and form things like rain and snow and fall back to Earth. So it's always moving more downward than upward. Okay, so on that note, we should talk briefly about weather and climate. So I know these feel like very Earth-centric ideas, but we will encounter them on other planets and on moons as well. So anytime we have an object with an atmosphere, with gases or liquids surrounding it, the dynamics, the circulation of that atmosphere lead to what we call weather. And so on Earth, weather is primarily concerned with the density, relative density of air, and with the water vapor content of the air, right? We want to know if it's going to rain or not. And the way that this weather forms is through one, the heat from the sun. So that sort of powers a lot of this. That powers the water cycle, the evaporation. And also from the rotation of the Earth. So because the Earth is rotating, we have certain currents and types of circulation that like to form as these weather patterns develop. But in general, weather is really complicated, right? That's why we can only predict it about a week out. Any tiny mismeasurements in any of our data points cause wildly different weather to result. This is called the butterfly effect. You may have heard of this idea that if a butterfly flaps its wings in a forest, it jostles the air, and eventually that becomes a hurricane somewhere else. Maybe a little exaggerated, but not far off in terms of how complicated these dynamics are. Now, in addition to weather, we can also talk about climate. So climate is a long-term pattern. So for example, the climate in Southern California is sort of this very temperate, pleasant, warm, relatively dry climate. So climate tends to mostly depend on latitude and of course also on altitude. And it does change. So Earth's climate has changed quite dramatically. So during the time of the dinosaurs, it was much warmer. During the Ice Age, it was much cooler across the planet. But this tends to be a process that occurs over millions of years, or at fastest, tens of thousands or hundreds of thousands of years. We'll talk very soon about how humans have accelerated this process and sort of what that will lead to if we don't take immediate action, or maybe we're already locked into our fate at this point. But anyway, so weather and climate, these are the same idea, but different timescales. And we will see these phenomena not just on Earth, but also on other worlds as well. Okay, so kind of random, but this is the order of the book. So we're going to change gears a little bit and talk about the origin of life. And the reason we want to do this is because, as we'll see, it has a big impact on the atmosphere, actually, atmospheric composition. So life, the origin of life is something that's really miraculous. In order for life to form, we have to have a lot of things happen right. Of course, if life didn't form, we wouldn't be here to think about why it didn't. So that's something that we call sort of an anthropic principle. But in general, our understanding of the development of life on Earth is that sort of simple organic compounds could be formed in the early history of Earth when there was less oxygen in the atmosphere. These compounds would be unstable today, but they were more stable back then due to the lack of oxygen. And through just random chemical reactions, eventually you start to get more complicated things like proteins. And finally, you get something like RNA or DNA, which allows for self-replication. So RNA and DNA are just special molecules. They're just chemistry, but they have this wonderful property that through what we call mitosis in a cell, they can split apart and duplicate. So once you have a complicated structure, you don't just lose it, or you don't just get one of them. They can start to form more and more and more and take over the planet, and here we are, right? So this process took at least hundreds of millions of years, if not a billion years, to form. But once we get this self-replication, it really accelerates and we get the variety of life we have today. But what you should remember is that for the first many billions of years of life on Earth, it was really just bacteria, right? Or even simpler types of organisms. We only get complex life after the Cambrian explosion, and we'll see sort of when that was and what that entailed really briefly. So how does the origin of life connect to the atmosphere? Well, it turns out Earth's atmosphere has changed quite a bit over its history. So we can split it up into different eras, starting with the Hadean era, named after Hades, right, the underworld. That's when Earth was really young, and basically whatever gases were part of the solar nebula were pulled by gravity to the surface. Earth was still like a molten, ball at this point, and so that gas was blown away by the solar wind, and it didn't last very long, only a few 100 million years, and it had a composition that was mostly hydrogen and helium, the same things that the gas giant planets are made of. After that, as the Earth cooled, the rocks, these volcanic rocks, let gases out. So gases that were bound to the rocks were able to escape, and that produced the secondary atmosphere around 4 billion years ago. And that's the atmosphere that life was able to start forming in, right? This is where we had very little oxygen, so these more complex molecules could form and not react away immediately as they would today. After life forms, which takes a few hundred or maybe a few 100 million or maybe a billion years, we start to see the atmosphere change again. This is the methane era, around 3 billion years ago. And that's where the first bacteria, which were anaerobic bacteria, so they didn't need oxygen. We still have some of these guys today, but they're pretty rare on the surface. So these bacteria tend to make methane, and we actually see that signature in Earth's atmosphere as it starts to have more and more methane. Then the most important, if you only remember one thing from this slide, the most important era or event in the history of Earth's atmosphere was called the Great Oxidation Event, or GOE. And this occurred about 2 billion years ago, and this is where we start to get cyanobacteria. So basically the precursors to modern like algae and plants and things that take in molecules like carbon dioxide and release oxygen. And so this is where the oxygen content of our atmosphere came from. It came from these living creatures. And after the oxygen built up, around 500 million years ago, this is where we get what's known as the Cambrian explosion. That's where there was enough oxygen to finally support more complex forms of life. So we get all sorts of things, mostly in the oceans. So little shrimps and this is where trilobites really take off if you're a fan of trilobites. All sorts of fun things, opabenias. Anyways, so I say all this, as an astrophysicist and an astronomer, this is interesting to us because when we look at other planets, again, right, we're using Earth as a laboratory. When we look at other planets, we can use their atmospheric concentrations, the composition, to understand, is there life on this planet? What has happened in its history? And to try to find clues about this planet, any planet's development. Okay, so I said earlier that I'd mention it, so let's talk about it now. The greenhouse effect. You've probably heard of this in the news at some point, but due to the fact that we spent some time talking about the electromagnetic spectrum, I want to help you understand this in a much deeper way, a much more meaningful way, so that if someone, doesn't understand it or thinks that all this climate change stuff is fake, you can try to maybe help them, see the light, so to speak. So what's going on in the greenhouse effect? Well, it all comes down to this idea we had last week that different wavelengths of light, they're the same thing, they're the same substance, they're just vibrations of electromagnetic fields, but they interact with matter very differently. So we take for granted the fact that air is transparent, right? We can see through the air, but that is only true with certain wavelengths of light, right? We saw last week that only visible and radio waves and a little bit of infrared is able to pass through the air. And so that's why when we want to, build an X-ray telescope, we have to put it in the upper atmosphere, on some sort of spacecraft. So the greenhouse effect works via a very similar mechanism, basically. So whenever sunlight passes through the atmosphere, most of it makes it through because air is fairly transparent to visible light, and the sun mostly is making visible light. When that visible light hits Earth, when it hits the rock of Earth, for example, it's absorbed, and that causes this rock to vibrate. Now it becomes a black body object, right? It releases a black body spectrum, which is centered around the infrared. The Earth is not as hot as the sun, so it doesn't emit as high a frequency as the visible light from the sun. It emits a lower frequency. This is why we get infrared. This infrared radiation can also escape into space. However, gases like carbon dioxide are transparent to visible light, but not to infrared light. They block infrared light. And so the more carbon dioxide there is in the atmosphere, the more of this infrared light that's emitted from the rock is trapped like a blanket underneath this layer of carbon dioxide. And that causes the Earth to heat up. Now, this is exactly what happens in a glass greenhouse as well. Glass is transparent to visible light, but opaque to infrared. And so this is why we can make a greenhouse that's much hotter inside than it is outside. It doesn't need any heating element. It's just, it's like a one-way valve. It's letting more energy in than it's letting out. So that energy builds up inside. Now, how is this connected to humans? Well, humans, we like energy. We like, having lights and, listening to Zoom lectures about astronomy. And so to get this energy, we've taken a bunch of fossils, right, fossil fuels from the dirt, and we've burned them. And when we do that, we release carbon dioxide at a rate that has not been seen in the history of Earth before. And so what this means is that we are changing the climate of Earth. We're causing it to get warmer at a rate much, much faster than natural climate change. So just over the last 100 years, the temperature of the Earth on average has changed by about 1 degree Celsius or so. And that doesn't sound like much, but a lot of processes, so things like coral reefs and rainforests and so on, are very sensitive to climate. And a lot of weather patterns that humans and animals rely on are also very sensitive to these changes in climate. So as we change the climate rapidly, not only are we, causing ice to melt and sea levels to rise, but we're also disrupting, migratory patterns. We're disrupting different weather phenomena. We're making storms that do occur maybe more intense because they can build up more energy due to this increased heating. And basically, we're making life on Earth harder for a lot of other species and also for us. So what does this mean? Well, if we keep burning fossil fuels, the Earth will be okay. The Earth will still be around, and some creatures will maybe still be okay, and they will eventually evolve and, repopulate Earth with plenty of different species. But the species we know and love now are not going to make it, and a lot of humans will, have a much more miserable life as a result of this change in climate. And so, we should take this as motivation to do better, to change to renewables. And that's really something that has to happen at a societal or governmental scale, not just an individual scale. Okay, so enough of my soapbox here. But we should continue on talking about using Earth as a laboratory for other planets. And so we're going to go back to the crust, and we're going to start to think about where are the craters on Earth. So you may know meteorites are what happens when small rocks from space come down and hit Earth. And Earth is pretty old, right? 4.5 billion years roughly. And so as we talked about before, maybe we want to use Earth as a place where we can learn about other planets and try to apply these lessons more broadly. So when we look at planets like Mercury, we see a lot of craters, not so many on Earth. So where are they? Well, they've they've been formed and then erased is the short answer. Basically, because Earth has weather, and also because we have plate tectonics and volcanoes and subduction zones and all these things, a lot of these craters have been made invisible. In addition, 70% of Earth is covered in water, so if something hits the water, it tends to not leave much of a trace. And we also have significant parts of the land covered by forests or plants that can similarly obscure any crater marks that would otherwise be visible. So this picture is actually of a crater that was formed around the Cretaceous era, not the one that killed the dinosaurs, but a different one. And we can see that just in that relatively short, geologically speaking, period of time, that it's almost been erased. We can barely see this circular crater anymore, just after maybe 70 million years, which, compared to 4.5 billion is not much at all. Okay, so do we have any more recent impacts? Well, we have a few. So one that's really cool and I would encourage you to read about is the Tunguska event, which happened in 1908 in Siberia, luckily, a very low populated portion of the surface, where what was likely a comet but could have been a small asteroid impacted Earth in the forest. And it actually didn't quite impact Earth. It burnt up in the atmosphere, but it had enough momentum that it created an explosion, like an airburst bomb. And it was equivalent to a fairly large nuclear explosion. Very energetic phenomenon. Luckily, there aren't many people in Siberia, so I don't think it was too detrimental. But if that happened over a modern city, it could easily kill tens of millions of people. Okay, another example is Meteor Crater, which is the name. It's also called Barringer Crater. And this is one of the most beautifully preserved craters in the world. It's fairly nearby. You can go drive out to it in the desert. And we were actually able to recover meteorite fragments from it as well that were iron nickel composite material. And this crater, we estimate, is about 50,000 years old. So that's likely before humans were in North America. So no people would have been here to see it, but certainly, animals, maybe some woolly mammoths or something would have been around to see this huge explosion and this crater being formed. So this structure down here, you can see there's a road and there's a pretty large museum building, just to give you a sense of scale here. Okay, so speaking of impact craters and also speaking of our current destruction of the planet through climate change, it's good to know that there have been a few mass extinction events in the history of the Earth. Scientists like to call them the Big Five. And these help us understand, so despite the fact that these impact craters are often washed away by weathering and erosion, these mass extinction events, we can see them in the fossil record, and they can help us gain some insight into this, violent history of Earth. And so what we see is that in all these cases, at least 3/4, and in some case, particularly the third, which was the worst one, 95% of all species went extinct. And the reason this happens is that evolution is very powerful, but it's also pretty slow. Tends to take on the order of hundreds of thousands of years. And so when we have a rapid change in Earth's climate, usually due to either an asteroid impact, a bunch of volcanic eruptions all happening at once, or some sort of complicated climactic feedback loop, when one of these events happens, we can get a rapid change in the climate, just like we're seeing today due to humans. And evolution can't keep up. So a bunch of animals that evolved for their particular habitats suddenly can't survive in them anymore, and they go extinct. And so when that happens, whatever few species survive, they manage to, retake over the planet and maybe have some time to themselves. Eventually, they evolve and split into more species, and then we repeat the cycle again, maybe in a few 100 million years later. And so the most recent of these was the extinction of the dinosaurs roughly 65 million years ago. And that was the extinction where a few little rats and other mammals managed to survive. And that's how you and I are here, right? They eventually evolved into all the mammals we see today. And so how did that rapid climactic change occur? Well, we now are pretty sure that it was due to a big asteroid hitting roughly in the Yucatan Peninsula in Mexico, leading to this crater that we can actually barely see. It's almost been washed away, but we can kind of see the evidence of it today. Some of it's underwater, which is the Chicxulub crater. And when that asteroid hit the Earth, it made a debris cloud so large that it covered most of the planet, leading to decreased sunlight levels. So a lot of plants died. It changed the atmospheric composition. A lot of bad stuff if you're a dinosaur. And one of the things that it did was it left a layer of iridium, very thin, fine layer of this metal, which is otherwise very rare on Earth. And that layer, it just happens to sit right when all the dinosaur fossils stop appearing in the sedimentary layers. It gives further evidence that this impact crater is associated with the mass extinction of the dinosaurs. Okay, so how is this relevant to us as humans? Well, of course, the mass extinction that we're causing with climate change could, and most likely will, kill many people. But we could also have a mass extinction due to an asteroid impact, and so it pays to be prepared. Now, asteroid impacts large enough to cause a mass extinction are pretty rare, every few 100 million years or so. But these days, we have the technology. We're able to track asteroids if they get close to Earth, and using supercomputers, we can predict what path they will take. And whenever we see an asteroid that's on a path that will bring it close to Earth, we can start to prepare. And if it looks like it might hit Earth, we can actually start to implement some strategies to make it go somewhere else. Okay, so because orbits are very predictable using the laws of physics, what we can do is we can change the orbit very slightly, but if we do it early enough, then this can cause something that would have hit Earth to miss Earth instead. And so we can do that by colliding spacecrafts into these asteroids, or by connecting them to the asteroid and then using the thrusters of the spacecraft to try to push them in a certain direction. We can also, the good old-fashioned take a nuclear bomb and explode it nearby method. Always, a good thing to have in our back pocket, considering we have a few thousand nuclear missiles on Earth. And so through a combination of these, the one I highlight here is the DART program. We hope to have, by the next time there's a large asteroid on a path towards Earth, we hope to have a nice strategy to deal with it. Okay, so that's where we're going to leave off for Chapter 8. Hopefully you've learned a little bit about our planet, and I hope you remember that we are a part of space too. Just because we live on Earth doesn't make it any less a part of our solar system, and therefore a valid site of inquiry for the science of astronomy. But we want to take these lessons from Earth and we want to apply them to other planets, and that's what we will do in the next chapters. So I'll see you there.